So hi everyone to today's Tech Talk about k0smotron again, day 2 operations and cluster lifecycle management. Today's talk will be presented by myself, Julian Hennig, Senior Solutions Architect working at Mirantis and based in Germany. If you want to reach out, feel free to use my email on GitHub or LinkedIn. And with me, my colleague Jussi Nummelin. Over to Jussi.
Hey everyone. So I'm Jussi, also from Mirantis, working as a senior principal engineer, leading the K0s and k0smotron engineering efforts.
So let's get started. And today we will cover, first of all, a quick explanation on what day 2 operations are. So what do we understand as day 2 operations? Again, a quick reminder or a quick summary of what k0smotron and Cluster API are, and how those two projects can help with day 2 operations. At the end, we will have a Q&A session, but for the day 2 operations, we will also see a demo, a very enhanced demo, advanced demo that I'm looking forward to from Jussi.
Need to learn Kubernetes quickly? Check out our free ebook with hands-on exercises you can complete on your laptop over a short break or lunch. Visit mirantis.com/learn K8s to download now.
So first of all, let's talk about day 2 operations. Basically, when we talk about day 2 operations in relation to Kubernetes, there's the headline cluster lifecycle management. And some of the topics that I've listed here can be already cluster lifecycle management, let's say, tasks. One, for example, can be scaling or autoscaling based on metrics or configuration that you've applied to the autoscaler. Observability, of course, so anything on metrics, logging, monitoring, alerting, but also tracing is part of observability. When it comes to security, of course, you need to do security patches, have a look into that your clusters are compliant, or you react on compliance changes. Backup and recovery, of course, are very important. Disaster recovery when it comes to any failures or problems. Updates and upgrades. Everyone knows that Kubernetes is a very fast-moving project. So, of course, these need to be looked into too. And we have troubleshooting and support. So everything that is day 2 operations basically is keeping the lights on and enhancing the platform, or keeping an SLA, for example, of 99%. Of course, all these tasks adding complexity and can be very hard for a team to manage. That's something where different projects can help. Today, we will talk about 2 of them, more precisely about k0smotron and Cluster API. Of course, this list is very long. That's why we have a shorter list now. So we will just look into cluster lifecycle management and autoscaling and updates and upgrades. But there will be a 4th part of this Tech Talk series where we will talk about observability and other topics too. But since it's a very complex use case with cluster lifecycle management and autoscaling with Kubernetes, we'll just look into k0smotron and Cluster API and how they can do cluster lifecycle management together. So as a reminder, k0smotron and Cluster API are both open source projects and basically desired to do cluster lifecycle management. k0smotron, as mentioned in a couple of other tech talks now already, is some kind of controller manager, control plane manager, or you can also say, of course, Kubernetes in Kubernetes. It offers the benefits of open source Kubernetes because, of course, we are using K0s here, and K0s and k0smotron have a lot of out-of-the-box data operations features already included. We also have Cluster API. Cluster API is a sub-project of the Kubernetes community, or short CAPI, which lowers the burden for cluster lifecycle management and especially for multi-cloud lifecycle management. So a lot of different, I would say, pros in Cluster API that will definitely help us do data operations with Kubernetes. But let's look into how they both work together. So this is just a small architecture diagram that shows the management cluster and a child cluster, both Kubernetes clusters. And the management cluster has in total 3 components here, the blue ones. It has the k0smotron controller, the cluster API controller, and the cluster API infrastructure controller. So when we talk about k0smotron and cluster API lifecycle management, in k0smotron, there's a very, let's say, unique functionality because of K0s. So K0s is an optimized, a lightweight Kubernetes solution that is shipped in a single binary. And thus, we have the big opportunity here, or the chance to do or run the control plane of a Kubernetes cluster in a container. And that's where k0smotron can help, and k0smotron can manage these K0s control planes. So the child cluster here on the right consists of the K0s control plane running as workload in the management cluster and the worker nodes running in any infrastructure provider or on any infrastructure. The control plane consists of 3 components. The pod itself with the container, of course, or containers. We have the service, a load balancer service that is exposing the Kubernetes API and other components. And we have volumes in this case. With K0s, we have the big benefit of not only etcd, but also a lot of other possibilities that we will look into the demo here as well. Like, for example, using Postgres for the cluster state store. But if you're using etcd, you can use persistent volumes in your Kubernetes cluster to run the cluster state store. Now, the cluster API controller does manage the infrastructure outside of the management cluster and inside of the management cluster. So in this case, we are leveraging k0smotron as an infrastructure provider for cluster API and the infrastructure controller for any infrastructure provider to provision worker nodes outside of the management cluster. And Cluster API does the magic in the background to put everything together. So we have a full child cluster running only with the worker nodes in the desired infrastructure and the control plane running in the management cluster. How does that work? Specifically, when we are talking about cluster lifecycle management. A lot of concepts, especially one that we will talk today about is the controller concept or operator concept. And it's all based on reconciliation and reconciliation loops or control loops. So we will look into very quick into decorative APIs, into CRDs and reconciliation, and then how Cluster API and k0smotron combined give you cluster lifecycle management. First of all, when we talk about decorative APIs, we are talking about YAML files. So if you want to create a new cluster, for example, if you want to create something new, of course, there needs to be something in YAML with Kubernetes. That is where CRDs and reconciliation comes into play. So in this case, we're talking about the operator concept and about custom resource definitions. So an operator is a combination of the controller and a custom resource definition. So when we are talking about Cluster API or about k0smotron, we have, for example, a cluster as a custom resource, and the operator or the different operators and controllers will look for the different custom resources they are responsible for and apply them to Kubernetes. Either schedule something on worker nodes or, for example, talk to an API outside of the management cluster. Cluster API itself has different controllers that are very important here today also. So first of all, we've already talked about the Cluster API controller, which is the central manager or controller. And we have 3 other controllers for different purposes. We have the infrastructure controller that I've already mentioned that will handle the interaction with the desired cloud or private cloud. Can also be just vSphere or OpenStack or any other public cloud like AWS, GCP, or Azure. We have the Bootstrap controller, which is responsible for worker nodes. And we have the control plane controller, which is responsible for, of course, the control plane. With k0smotron, I've already mentioned that it is possible to create the control plane inside of the management cluster as some kind of workload, so running as pod. But that's not the only option. With k0smotron, you can also create a full-blown Kubernetes cluster with 3 control plane nodes and as many worker nodes as you like outside of the management cluster. So that is also possible. When we now talk about cluster lifecycle management, the combination of both, of course, of Cluster API and k0smotron give us a very unique way for cluster provisioning. So more for day 1, but also for day 2 when it comes to other cluster operations. Like, for example, upgrades or updates. That's where Cluster API and k0smotron can help with. But also something that's called K0s Autopilot, which we will look into our next talk a bit deeper. But Jussi will today explain a way to upgrade a Kubernetes cluster just by modifying a YAML file. And we have scaling. And scaling is a big topic, especially because this week is Black Week. And you can imagine how many Kubernetes clusters are currently scaling up and down in different environments. So if you want to have an easy way to do cluster autoscaling, there's something in Cluster API or on the Kubernetes native community project already, which works very well with k0smotron and K0s. But enough talking, sorry. Let's go into the demo. We will have a look into creation of a cluster. The control plane will in both cases run in Hetzner, in the management cluster. And we will create 2 clusters, one with worker nodes outside of Hetzner and AWS, and one with nodes in Hetzner directly. Scaling the cluster will be one part, so manual scaling, then also auto-scaling. I've mentioned cluster upgrades. Perhaps if we have time, we'll have a brief look into cluster stage options and some goodies or good to knows at the end of the show as well. But over to you, Jussi, to show us the demo.
All right, thank you, Julian, for the presentation. So, cluster API and provisioning clusters with K0s and k0smotron. So, as Julian mentioned, everything is fully declarative, and as mentioned in the world of Kubernetes, declarative essentially means a lot of YAML, unfortunately. But YAML is very readable for us humans, so that's pretty fine. So let's look at a quick example. So what I basically have is a definition for a cluster. So cluster API, for those who haven't been working with cluster API that much, cluster API is kind of divided into abstract types and then implementation specific types. So of course, on top of everything is something that defines that okay, we are actually creating a cluster now. And then of course, like in any Kubernetes object, you give the object a name, namespace, and then further configuration for things that it's controlling. So in this case, I'm basically saying that I'm creating a cluster, and the control plane will be implemented by something called k0smotron control plane, and then the infrastructure reference basically tells that okay, rest of the infrastructure is going to come from Amazon. Going forward with the k0smotron control plane definition, of course, I need to define that what version of K0s and k0smotron control plane we want to run for the cluster, what type of persistence we use for the control plane. In this case, of course, I want to use persistent volume claims so that I can actually keep the state while for example, upgrading the pods that are actually running the control plane. And then I want to expose the control plane, basically the API server, using a load balancer service. And then for my specific cloud provider that I'm using for the demo, you can specify further annotations for the service object that will be automatically created by k0smotron to further configure the cloud infrastructure specific things. In this case, I'm just saying that, okay, let's create the load balancer in one specific region. For the Amazon parts, I'm going to basically use an existing VPC, an existing subnet in EU Central 1A zone. So for the demo purposes, I'm keeping things very, very simple. So I'm using only one subnet and one zone. But of course, you could then list many other subnets and zones and whatnot. Like I said, in cluster API, things are always, well, not always, but most of the things in cluster API are divided for abstract concepts and then implementation specific things. So a machine is a very abstract concept in cluster API, because of course the cluster API itself doesn't really know how this machine will actually be spinned up and where it's going to be kind of like, in a quotation marks, implemented. So I'm telling that okay, we have one machine, and again, name and namespace for the object, to which cluster this machine it connects to, what's the failure domain, well, basically the same zone. How do we bootstrap, configure the node, and this links to, again, k0smotron and K0s. So we're basically saying that okay, when we are about to bootstrap this machine, let's use K0's worker config object for that. And then I'm saying that, okay, this abstract machine thingy will actually be implemented as Amazon machine. So basically EC2 virtual machine. And then for the Amazon specific parts, I'm basically defining only which AMI to use. I'm using Ubuntu 2204, what instance type, what IAM instance profile to use, and then some additional flags to simplify things for the cloud init. And then again, I need to tell that, okay, in which subnet I wanna spin this up, and which security groups to attach to the machine. And of course, if I need to debug something, I want to attach my own SSH key to that machine. And then finally, the K0s worker config object defining what do we run in the machine when we create it. So by default, everything has same defaults in K0s and k0smotron, so I'm not specifying anything further into the definition. But of course, here you could define like all the kubelet flags, all the K0s worker configuration options. And then as usual, kubectl apply it. A lot of resources are created. And now, because I'm using ready-made infrastructure on Amazon, all the VPCs and everything are readily available. I need to actually manually patch the Amazon cluster object to have a ready state, because I don't want for this simple demo, I don't want the Amazon infrastructure provider for cluster API to go and configure all the VPCs and everything for me. So that's why I have to manually patch it now. And if we look at some of the things, so the cluster level object says that, okay, the cluster, the very abstract high level things are provisioned. We have a machine that's still in pending state, which means that we're actually waiting for the other different various cluster API controllers to do their job. So cluster API in general is like there's a lot of smaller controllers that are doing bits and pieces here and there. So it's more like a puzzle in a way, especially if you have to debug something. So the node is actually now provisioning. So basically we're now waiting for the EC2 instance to actually boot up. And while waiting for that, like Julian mentioned, k0smotron has this unique feature of being able to run the control plane in a pod. So if I look at my pods on my default namespace, I see a pod called KMC K0s Amazon test 0, which is actually running the control plane for my cluster. And then of course, like Julian mentioned, if we look at the services, there is a service somewhere. Yeah, this one. So this one exposes the Kubernetes API for that control plane instance. All right, let's see if the machines are up and running. All right, we see a provider ID, Amazon something, which means that the EC2 instance is up and running. And I think this already highlights one of the really, really cool and nice aspects of k0smotron. I'm running the control plane now on one cloud provider. The workers are on different cloud provider. So you don't have to use same cloud provider for control plane and worker plane. All right. Of course, we want to look at the child cluster itself, right? So cluster API comes with a command line tool called clusterctl, clusterctl, get kubeconfig k0s AWS test, and let's pipe it to my normal kubeconfig location, AWS test.conf. All right. And then what I can do is I can go to my lens catalog, and I see the file there. I can actually connect to that cluster. And voila, my lens is now looking at the child cluster, which has one single node as the workers, because, well, like you saw in the YAML, I only defined that, okay, there's one machine part of this child cluster. All right, so control plane on one provider, workers on different provider, pretty simple with bit of YAML. Well, bit of YAML. But pretty, I would say, pretty straightforward YAML, at least. All right, so let's look at a bit more complex example. So in this case, I'm going to create the control plane again using k0smotron in this running as a pod or set of pods in this mothership cluster. And then I'm going to run the worker nodes also in the same Hetzner provider. But like you saw, the provider doesn't really matter which provider you use. All the YAMLs for cluster API is pretty much the same, of course, still. So same things, cluster, k0smotron control plane, reference to an infrastructure. And again, K0's worker configuration. This case, it's a template type of an object, which I'll explain in a bit why. And here you see that you can actually enable all the needed K0's worker configurations also in these worker config objects. And why we are using a template type now is because of this. So instead of provisioning one single machine, I'm actually creating a machine deployment. And what machine deployment is, well, those I would guess that most of you are pretty familiar with Kubernetes based concepts already. So a machine deployment is essentially like a deployment is for pods. So machine deployment manages and orchestrates multiple machines. So hence the word template. I have some autoscaler annotations, minimum size 1, maximum size 3, and then typical labels. I have specification for the machine deployment, which has another template, which is specification for the machines that are created out of this or based on this template. And then again, the same kind of references, which cluster these machines are part of, how they are going to be configured, bootstrapped, how they are going to be implemented on the infrastructure level. That's about it. On the Hetzner machine level, I'm just saying that, okay, which image to use, which type to use, and again, which SSH key to configure to the machines. Again, let's apply it. Bunch of things are created on the API. Bunch of objects are created on the API. Let's switch to the Autoscaler test namespace. Some things are still provisioning on the cluster level. Basically, we're waiting for everything to boot up on the control plane first, of course, and in a 20 or 30 seconds, everything is provisioned on the high-level cluster level, and then we're seeing that we have one machine that is created out from the machine deployment. Because I didn't say anything about the replicas yet, so everything defaults like in Kubernetes pod deployment. It defaults to having one. It's pending, so we're essentially waiting for the different cluster API controllers to orchestrate things, create the bootstrap configuration and whatnot. It takes usually a minute or two to actually get the node up and running. Like I said, machine deployment behaves pretty much like a deployment for pods. So you have replicas, how many are available, how many are unavailable, whether it's scaling up, scaling down, the usual things for a deployment. Yeah, everything looks pretty okay. Bootstrap secret is created, so the machine should be okay. So some glitch somewhere. Maybe the Hetzner thing wasn't able to talk to the API or something. So using machine deployment, created one machine, which we can of course now go and edit. So let's say that we want to scale up, for example. So we can go and edit the machine deployment. Let's use Lens to do that. Replicas, where is the spec? Replicas here. Let's say 2 replicas. Save, close. We see that the machine deployment itself is updated to have 2 replicas, and we're provisioning a second machine now because we already had one, so we need to add one more. Okay, that was fast. So we have 2 machines now running on the child cluster. What I've already deployed beforehand is Autoscaler. So I have the Autoscaler deployed already to the Autoscaler cluster namespace that I used for all these cluster API objects. So, but we'll have everything info how to deploy and configure the Autoscaler itself also in the repo, where we'll post all these example YAMLs and everything to run the demos. But it's just the standard Kubernetes Autoscaler. So let's grab the kubeconfig again. clusterctl get kubeconfig, and that was autoscaler test. And let's pipe it to, and it's in the namespace autoscaler test. Let's pipe it to kube autoscaler test.conf. kubectl kubeconfig, grab that file. So I'm using kubectl, using the autoscaler child cluster as the kubeconfig file. Get node and pod on all namespaces, and we see that okay, there are the 2 nodes. There's the typical things running on the cluster, core DNS, kube proxies, CNIs, and whatnot. And this create container configurer now reminds me that when using cluster API, you always should deploy the cloud controller manager for that infrastructure. So now, for example, I'm running these worker machines on Hetzner, so I need to deploy the Hetzner cloud controller manager into the child cluster. Well, it's actually already deployed, but it's failing to create the container, but because of course it needs some API token to talk to the Hetzner API. So I need to patch that secret into place. All right. So machine deployment, 2 replicas up and running, 2 are up to date. Fantastic. So let's have a quick look at how to upgrade things. So and as you know, when things are fully decorative, upgrading things like for example, you're upgrading your container image in your pods that are managed by deployment, it's just changing one string, basically one version string in the YAML. So just as an example, autoscaling, that what the autoscaling.yaml was the original one, and then if we compare that to autoscaling Autoscaling upgrade. You see that I'm just changing versions. I'm changing the control plane version to 128.3, and then on the worker machines and templates, I'm changing also to 128.3. So if we now apply the updated one, we change the object on the Kubernetes API. You already see here that the machine deployment is actually scaling at 3 replicas currently. So what it's actually doing is exactly the same thing that happens to your pods when you change, for example, the image that you're running in the pods. It's creating one new, deleting one old, creating one new, deleting one old. So exactly the same thing happens now here. We see that one machine, the newest one, is on 128, and soon we should get rid of one older one. It just took a while for Hetzner and the Cloud Controller Manager to actually connect that this machine object in the mothership cluster actually maps to this node object in the child cluster. And now you see that because one was updated already, and we've said that there's 2 replicas in the machine deployment, you see that one is now actually deleting. And unfortunately now deleting actually takes a bit because cluster API does it in the safest possible way, meaning that we'll first wait for the node to drain all the pods away. Then we have to wait that everything boots up in different nodes and so forth. So it does all the draining, cordoning dance for you automatically. Now it's provisioning one new machine for 128.3 and so on. So it'll do the rolling upgrade like it does for, like Kubernetes does for pods when using deployments. All right. Get pod. What am I doing? I have somewhere this. So we see that some pods are still waiting to boot up and go away and so on. So the cluster autoscaler, like I said, that's already configured for this demo cluster. So what we can do is actually have a look at the simple Nginx deployment projects. Tech Talk, Autoscaling, Nginx. So what I did is that I configured each of the worker nodes to allow maximum of 15 pods per node, just purely for demo purposes, so that I can easily push it over its limits. Now we have 2 nodes, so altogether we have 30 nodes capacity in the cluster. So if I create a deployment and ask for 15 pods, we know that it's going to go over its limits. Apply -F. Nginx is created. Let's switch to the default namespace only. And as you see, what? No, but that was for a single node. I need to actually scale it still a bit, sorry. My math is not good either today. Let's push it to 43, for example. All right. So now we see that we are over our limits in the cluster. So some of the pods are now stuck on pending state. And this pods being stuck on pending state, that's a clear signal for the autoscaler that, okay, hey, there's not room enough in the cluster to run everything that has been requested. So the cluster autoscaler needs to do something. And in this case, of course, it needs to scale up. So if we switch to the mothership cluster and look at the machine deployment, it's scaled to 3 replicas already. But it's not going beyond 3, because remember this YAML configuration autoscaling. Remember this configuration, minimum size 1, maximum size 3. I'm just trying to save resources, so I don't want to actually scale to like 100 nodes. So that's why we are now at 3 replicas. 3 are ready, all 3 are up to date, and 0 of them are unavailable. So autoscaling works really, really nicely from the cluster API and cluster management point of view. And if any one of you have used the kind of the typical way of autoscaling with your existing clusters on existing infrastructure providers like Amazon or Google or whatnot, it's actually much more difficult to configure everything, because you have to point the autoscaler to different autoscaling groups and templates on Amazon side and whatnot. Because in this case, the autoscaler just looks at resources. It sees that we need more. It'll actually just go and change the replica count on this machine deployment object, and that's it. There's no more logic in the autoscaler when used with cluster API. So that's pretty cool. And at least in my personal opinion, it makes the understanding and usability of autoscaler much more simple. All right. So like Julian mentioned in the slides or during the slides, K0s and k0smotron is not only limited to use the traditional etcd as the state store for the cluster. So K0s itself comes with a component called k8s, which is kind of like a shim to use other data stores like SQL databases as the data store instead of etcd. So I have a quick demo for that. PG backend, PG cluster YAML. So I'm using the Postgres operator from the guys at Zalando. So I'm just creating a super simple Postgres cluster running on my mothership cluster. And of course, you don't have to use Postgres or MySQL running within your mothership management cluster. What you could actually use and what makes operations even a lot easier. Imagine you use something like Amazon managed Aurora database, because that has all the built-in functionalities, backups, restores, snapshots, whatnot. So why not, if you are running on that sort of a cloud provider that provides that service, why not leverage that for your Kubernetes clusters too? I have the Postgres database actually already running just to save a bit of time. And then if we look at the configuration from k0smotron point of view, again, all the typical cluster API things. I have a cluster, I have a k0smotron control plane, I have a Hetzner cluster defining the infrastructure for the worker nodes. But this is where things get interesting. So on the k0smotron control plane, I can define that okay, instead of running 1 replica only for the pod, run actually 2 replicas for the pods. And then we can point the k8s data source URL to this Postgres database that I've created. So, and of course, you don't have to have your secret in plain text. You can use actually secrets for this kind data source URL, but for the demo purposes, keeping it more simple to understand, I'm using plain text here. As you see, there's a placeholder which I'll soon substitute with the environment variables. But other than that, everything is exactly the same. I have Hetzner cluster, I have config templates, I have machine deployments with one replica, and so on. So from the cluster API point of view, nothing really changes per se. I'm just creating another cluster and the k0smotron control plane with quite different configuration. So what I'm doing now is I'm grabbing the password for the Postgres database from a secret that the Postgres operator creates and manages, and then substituting using env-subst to actually substitute it within the YAML itself. Just verifying that everything looks good. Yeah, looks pretty good. And then just pipe it to kubectl apply -f dash. That the last dash meaning that read the input from standard in. Again, all the objects are created. I have a machine deployment for the worker nodes with one replica. The cluster itself, provisioning, waiting for something to sync up on the infrastructure level. All the cluster API controllers synchronizing things, putting all the owner references on different objects and so on. Okay, cluster is provisioned. Machine is still pending. Again, waiting for things to synchronize between the different controllers. So these two are basically my two Postgres database nodes, pods running the Postgres database in clustered configuration managed by the Postgres operator itself. And again, I have this KMC PG test 0 and 1 pods. That's the k0smotron control plane running as a stateful set. Cluster PG test is provisioned, machine provisioned, waiting for things to synchronize again. Cluster CTL get kubectl PG test dot kube PG test cluster dot conf. And then if we open that with Lens, we have two nodes. But although we changed from etcd to SQL database as the backend data store for the cluster, everything is still exactly the same Kubernetes cluster and API. So you're not tied to using etcd with k0smotron and K0s. And one of the benefits is that now I can actually scale up the number of pods very, very easily. Whether I want to run one pod for the control plane, 3 pods, 5 pods, or how many I want or need to run. One of the troubles running etcd within a Kubernetes cluster, as we know, Kubernetes is very dynamic in nature. Pods come and go. An etcd cluster, well, that's not easy to configure in that way. So kind of externalizing the scaling of the data store and the control plane allows us, well, a lot more freedom in scaling things. And using, like I said, using managed services for the data stores and whatnot. So there's a lot of benefits in doing that.
So thank you very much for this demonstration. This great demonstration. Of course, some roadblocks are normal, and case sensitivity and exact names are very important in Kubernetes. Just a reminder.
Yeah.
So as a summary, we now just showed on try to give you a general understanding of reconciliation. Of course, how controllers and operators, what a controller is, what an operator is, and a bit about custom resource definitions. We talked about the cluster API operators or the different controllers for infrastructure, for the bootstrap and the control plane, and how k0smotron and cluster API work together in this regards. Like, for example, using the k0smotron controller for control planes in Kubernetes in the management cluster, and the k0smotron controller for worker nodes, for bootstrapping worker nodes. And of course, the traditional cluster lifecycle management things are really made easy in this case. So, of course, it's a big YAML file at the moment, but it gives you all the configuration that needs to be applied. And in combination, k0smotron and cluster API make it easy to scale up, to upgrade, to provision, to deprovision clusters, and to save time, definitely save time for you in operations. With k0smotron, we always mention resource consumption because the control planes you normally run either with other Kubernetes distributions do consume resources that are, from a point of view of business critical workload, are not really giving you big benefits. They just consume resources and of course offer you the Kubernetes API. But with k0smotron, that is something you can abstract and you can benefit from with the control planes running in the management cluster. And how cluster API can be extended. That's something we showed with our non-bloated but extensible Kubernetes K0s. So thank you for everyone listening and watching this recording. If you want to discover more, feel free to just browse to k0smotron.io. Of course, we also will share the GitHub link for the repository with everything that was shown by Jussi too, with all the YAML files, so you can test it by yourself if you want to. But also feel free to reach out to us to just ask questions or share any insights or any findings. If you find issues, use GitHub to file these issues. So feel free to interact with us where you want and where you can. Our next upcoming Tech Talks will be a Christmas special on the 12th of December with a little challenge coming from Center that will be hosted by myself. And there's an advanced day 2 operations session planned for January already, where we will cover some more of the day 2 operation topics that we've just mentioned in our slides and in this Tech Talk. Thank you very much, everyone, for listening in. Thank you for watching the recording, and have a nice day.